So let me introduce second speaker, Professor Srinivas. So Dr. K. Srinivas is working as a full professor at the Institute of Mathematical Science, Chennai, India. He is from Odisha. He did his BSc from GM College and MSc from Sambalpur University. He got his PhD from TIFR Mumbai under the supervision of late Professor K. Ramachandra. His area of interest includes analytic number theory, algebraic number theory, modular forms, and mathematical aspects of cryptography and digital watermarking. He has published more than 50 high-quality research papers in different journals of repute. Co-edited 2 volumes which were published in the lecture notes series of RMS, or Ramanujan Mathematical Society. He has guided 3 PhD students and many MSc students. He is managing editor of Hardy Ramanujan Journal and member of Board of Studies of many institutions. He has actively participated as a resource person in MTTS programs, INSPIRE programs, and coordinated many outreach programs in Odisha, along with his teacher, Professor Swadhin Patnaik. As part of academic collaboration, he has visited many places in India and abroad, which include Queen's University, Canada for 1 year, University of Turku, Finland, Department of Mathematics in Marseille, Bordeaux, Paris, Lille, Nancy, Genova, Rome, Parma, Pisa, Hong Kong, and many other places. In India, TIFR, HRI, IMA, ISI Delhi, IJR Pune, IJR Mohali, IJR Trivandrum, SRTM University, Andhra University. Finally, I would like to mention that he has conducted instructional school for teachers 3 times at KIIT deemed to be university, which were highly beneficial. It's an honor and privilege for being with us. Once again, I welcome you, sir, on behalf of the Department of Mathematics, KIIT deemed to be university. Thanks. So, sir, please, over to you.
Yeah, thank you, Dr. Vijjan. It's a pleasure for me. I hope you can hear me clearly.
Yes, sir.
Yeah, so it's a great pleasure for me, and thank you for the invitation. It's always nice to be at KIIT. I have several friends there, and I have a very close relationship with KIIT. I like that place and its ambience. So my talk is mainly addressed to students and research scholars. All right. So it's on the zeros of Riemann zeta function and its analogues. I request you to kindly, flash. Yeah, second one. Yeah. Okay. So my talk is on the following problem. As you have seen in the previous slide talk also by Professor Stephen Miller, the definition of Riemann zeta function, which is given by summation 1 by n to the power s, n is equal to 1 to infinity. Okay, and the series converges whenever the real part of s, which is sigma, bigger than 1, and it represents an analytic function. So Riemann studied this particular function. He wrote a paper which consists of 7 pages, Riemann's memoir. Okay, and this is the only paper in number theory by Riemann. He was known as great geometer and all, but this paper itself created, initiated what is now known as analytic number theory. So in this paper, he studied analytical properties of Riemann zeta function. And while studying the zeros of this function, he computed few zeros and arrived at a conclusion that all the complex zeros are on the line with the real part half. Okay, so zeta of beta plus I gamma is equal to 0 implies that beta is equal to half. And this, as you know, is called Riemann hypothesis. Yeah, next slide, please. Okay, and this is one of the most important unsolved problems in the whole of mathematics. Hilbert proposed 23 problems in the ICM of 1900. Okay, and this problem is one of them. Okay, it is still unsolved. and there is a huge bounty on it, named Clay Mathematics Institute, Cambridge. They have announced a prize of $1 million for a proof or disproof of Riemann hypothesis. That means you either show that it has infinitely many, all the complex zeros are on the line half, or you show that there is one zero which is not on the line with the real part half. All right, then you get 1 million at least. Okay, next please. So, okay, this Riemann hypothesis has several consequences. We will see some of them in few minutes. But the next step was taken by G.H. Hardy, okay, in 1914, who showed that the Riemann zeta function admits infinitely many complex zeros on the line with the real part s is equal to half. Okay, that is zeta s has infinitely many zeros on the line sigma is equal to half. This is known as Hardy's theorem. And in today's talk, I will be discussing about the classical proofs of this and a new proof of this, and also its extension, generalization to other L functions that we see in number theory. All right. So a little bit of motivation. Let us see why we study Riemann zeta function. Next, please. Okay. So you see the study of primes, it has interested many amateurs and professional mathematics since time antiquity. Okay. The first thing that we come to know in a formal way is by Euclid, which is in around 300 BC, which says that there are infinitely many primes. And I'm sure all of you know the proof of this. It's a very nice and one of the most beautiful proofs in mathematics. Namely, you assume that there are finitely many, and therefore you can write down all the primes, say 2, 3, 5 up to p. And then you look at the number n, which is take the product of all primes and add 1 to it. This will produce another prime, which is not equal to 2, 3, 5 up to p. And that gives you the proof that there are infinitely many primes. Recursively, you can, create one more prime with a given list of primes. All right. So this was about Euclid. Next, please. The next big step was taken in 1732 by Euler. All right. What he did was he considered S as a real variable. All right. And looked at the product, the infinite product consisting of the terms 1 plus 1 by 2 to the power s plus 1 by 2 to the power 2s plus 1 by 2 to the power 3s and 1 plus 1 by 3 to the power s, 1 plus 3 to the power 2s, and so on, so on, of all the primes. All right. And then you multiply this product. When you multiply this product, a typical term will look like 1 by p1 to the power some power, p2 to the power some power, p3 to the power some power to the power s. And the fundamental theorem of arithmetic, it says that every integer n has unique prime factorization. Therefore, each such product will give you 1k. All right. And therefore, when you multiply all of them, you will get summation 1 by n to the power s, where n is over all integers. And therefore, yeah, of course, you have to show the convergence of this. So whenever s is bigger than 1, the infinite product also converges and the series also converges. Therefore, they are equal. So therefore, this identity, summation 1 by n to the power s is equal to product p 1 minus 1 by p to the power s inverse. This holds whenever s is bigger than 1. Next, please. And from this, this Euler product, you can prove the infinitude of primes in one line. All right. See, on the left-hand side, we have a harmonic series, 1 by n to the power s. So as s goes to 1 plus, the series diverges. Now, suppose you had only finitely many primes, then the product will converge. Therefore, finite thing cannot be equal to infinite thing. So this is a contradiction. All right. So this is a one-line proof which comes from Euler's product. However, much more can be derived, which Euler did. He looked at logarithm of zeta function, which is the logarithm of the product, which is sum of the logarithms. If you remember, you have seen in Stefan's talk also. So therefore, if you look at this log of minus of log of 1 minus 1 by p to the power s, that you can expand as geometric series, because minus log of 1 minus x is nothing but x plus x squared by 2 plus x cubed by 3 plus all these things whenever mod x is less than 1. Therefore, the sum can be written as summation over p and then summation over m, 1 by m, p to the power ms. Now you split this sum into two parts. One part is where m is equal to 1, and the other part is where m is bigger than or equal to 2. So there are two parts, and in the left-hand side, you have log of zeta s. Okay. Now, as s goes to 1 plus, the left-hand side goes to infinity. Whereas the right-hand side will go to summation 1 by p, and then this second sum. So if the second sum is bounded, then the right-hand side will go to 1 by p, whereas the left-hand side go to infinity. So next slide, please. So you can show that the second sum is bounded. This is a trivial estimation. You just estimate things by taking absolute values. All right. You can stare at the screen. You'll see that if you take absolute values on the second sum, it is bounded by pi square by 6. So the second sum is bounded. Therefore, as s goes to 1 plus, the right-hand side goes to 1 by p, summation 1 by p, whereas the left-hand side goes to infinity. Therefore, in conclusion, summation 1 by p diverges. Now, when summation 1 by p diverges, that means there are infinitely many primes. All right. So we get much more than infinitude of primes. Infinitude of primes is derived as a consequence of summation 1 by p diverges. All right. Next slide, please. Now, the other important thing about this approach is Dirichlet in 1837, he introduced what is called Dirichlet characters and Dirichlet L functions. All right. And they looked at the series summation instead of 1 by n to the power s, Ls chi by n to the power s, Dirichlet L series. And then argued in the similar way like Euler. And he showed that this summation 1 by p, where now p runs over the residue class A modulo m. So whenever A and m are co-prime, this series diverges. All right. And this means that there are infinitely many primes congruent to A modulo m for any A co-prime to m. And this is a famous theorem. This is one of the biggest, very big result called Dirichlet theorem on primes in arithmetic progression. So take any arithmetic progression, A plus m, A plus 2m, A plus 3m. Whenever A and m are co-prime, you have infinitely many primes in this series. All right. Next, please. Yeah. Now, how zeros of Riemann zeta function are related to the study of primes. Again, Gauss, at a very young age, he was interested in the distribution of primes. So let pi x denotes the number of primes up to x. All right. Then he conjectured that pi x behaves like this logarithmic integral, which is 2 to x du by log u. So if you expand it, you will see that the first term is x by log x. Second term is smaller than that, that is x by 2 log x square. Third term is much smaller with denominator log x cube and so on and so forth. All right. Therefore, in general, pi x is asymptotic to x by log x. All right. So this is a conjecture of Gauss. Next slide, please. Okay. And Chebyshev, later, he showed that, in fact, if you take limit x tends to infinity, pi x by log x tends to 1. All right. So this is known as prime number theorem in the elementary language. Pi x is asymptotic to x by log x. All right. But the actual formulation of prime number theorem is slightly different. All right. So before going to the actual formulation of prime number theorem, let us define two more prime counting functions, namely theta x, which is Chebyshev's function. These are prime counting function with a weight log p. So theta x is p less than or equal to x log p. And psi x, this counts primes, not only primes, but prime powers also. So p to the power m less than or equal to x log p, and m is bigger than or equal to 1. So we will call it as lambda m. All right. Next, please. So the prime number theorem now is equivalent to the following statements. Given any x, real number x, there exists positive constants C1, C2, C3, such that pi x is asymptotic to this integral 2 to x du by log u with the error term O of x e to the power minus C1 square root of log x, or you can, in terms of theta x, it is x plus O of x e to the power minus c square root of log x, or in terms of psi x, x plus O x e to the power minus this constant times square root of log x. Now, if you assume Riemann hypothesis, all right, that is no zeros to the right of the line half, then you get a much better error term. These O terms are called error terms. Namely, psi x is x plus O of x to the power half times log x square. All right. Now, the first three formulas, they are derived unconditionally on the fact that the Riemann zeta function has no zeros slightly to the left of the line 1. See, the Riemann zeta function has no zeros on the line 1 or to the right of line 1. But if you can show that there are no zeros to the left of the line 1 slightly, then you get a prime number theorem. In order to get this prime number theorem with error term x to the power half log x square, you need to use Riemann hypothesis. Namely, there are no zeros to the right of line sigma is equal to half. All right. You get a much better, the best possible error term. Next, please. Okay. Now, prime number theorem, which was proved in last century, it has many applications. Okay. For example, this prime number theorem, as I said, the first error term depends on the non-vanishing of the zeta function to the left of the line 1 minus d by log t. All right. And this in particular gives information on the distribution of primes. For example, if you write down the primes P1, P2, P3, just a 3, 5, 7 in that order, increasing order, then look at the difference between n plus 1th prime and nth prime. Then the result says that they are bounded by Pn to the power 7 by 12 plus epsilon. All right. Whereas if you use Riemann hypothesis, you will get a much better bound, saying that Pn plus 1 minus Pn is bounded by Pn to the power half plus epsilon. So 7 over 12 is 6 over 12 plus 1 over 12, whereas it is only 1 by 2. All right. It's a much better result. Next, please. Next one is, for example, in cryptography, one would like to know, given an n, when n is a prime number. And one of the result is n is prime if and only if the Euler function phi of n is n minus 1. Because phi of p is p minus 1. It holds for no other integer, no composite number. All right. Now, in fact, this is a primality test that I have written down here. If you have an a which is co-prime to n, and if a to the power n minus 1 is 1 modulo n, but a to the power n minus 1 by q is not 1 modulo n, for all prime divisors of n minus 1, then n is a prime. That means a must be a primitive root modulo n. So therefore, the question is, given a prime p, how hard is to get a primitive root? Unconditionally, to find a first primitive root, you may have to go up to p to the power 1 by 4 square root of e. That means a power of p. But again, under a Riemann hypothesis, this is GRH means generalized Riemann hypothesis, you have to go only up to a log p square. So it's a power of prime here unconditionally, and here it's a power of log p, and it is much more efficient. So finding primitive roots are much easier if you assume Riemann hypothesis. Therefore, proving Riemann hypothesis is an important problem. All right, next please. Okay, now come back to the proof of Hardy's theorem. So remember, Hardy's theorem says that the Riemann zeta function admits infinitely many zeros on the critical line. All right. The main idea is very simple. It follows from the real analysis. Suppose you have a continuously differentiable function in AB, and suppose it is not 0 in AB, then the mod of integral of a to b fx dx or integral of the mod of the function, they are same. Because the function is not 0, that means it doesn't change sign. Therefore, whether you take the absolute value outside or inside, the values are same. All right. On the other hand, if you can show that if the equality is violated, that means if they're not equal, that implies that the function changes sign somewhere. That means it has a 0 of odd order in the interval a to b. All right. This is the basic idea behind the proof of Hardy's theorem. All right. Now the question is, we want to show that zeta of half plus it has a 0 somewhere. All right. It's a complex valued function, but our theorem was for real value. All right. Next, please. So Hardy did a very beautiful, ingenious idea. All right. He looked at the functional equation of the Riemann zeta function. All right. So Riemann zeta function satisfies a beautiful functional equation, namely pi to the power minus s by 2, gamma s by 2 zeta s is same as the left-hand side replaced by 1 minus s, where gamma is the Euler's gamma function. All right. Now rewriting the functional equation as zeta s is equal to chi s zeta 1 minus s. All right. Rewrite this functional equation as zeta s is chi s zeta 1 minus s. All right. And the properties of gamma function will tell you that chi of half plus it on absolute value is 1. All right. Okay, remember this one. Absolute value of chi of half plus it is 1. Absolute value. Next, please. So with this information, Hardy, he constructed the function z of t. Z of t is nothing but chi of half plus it to the power minus half, zeta of half plus it. All right. Now, if you take a bar of zt, conjugate of zt, you will see that this is same as zt. All right. By the properties written down in the previous slide, zt bar is zt. Therefore, zt is real for all real values of t. Second information is that since chi of half plus it is 1 in absolute value, therefore, absolute value of z of t is same as absolute value of zeta of half plus it. All right. So zt is a real valued function, whose zeros coincide with the zeros of zeta function on the line half. That means the complex zeros of the Riemann zeta function on the line half are same as the real zeros of zt. So that's how he got hold of the real valued function z of t and then applied the basic idea, namely whether there is a change of sign somewhere. All right, next please. So assume now that zt has finitely many zeros or no zeros. All right, and we will derive a contradiction. So if there are finitely many zeros or no zeros, then you can choose a sufficiently large, real number t naught, such that for all t bigger than t naught, your integral, the absolute value outside or inside, it will be same, right? Because there are no zeros of zt when t is bigger than or equal to t naught. All right. Therefore, okay. Now the idea is whether you can find a violation of this equation 7. If you can violate equation 7, identity 7, that will show that there is a small t such that z of t changes sign. And in other words, that means zeta of half plus it vanishes between t and 2t. And since t is arbitrary, there are infinitely many zeros. This is the Hardy's proof idea, basic idea of Hardy's theorem. Next, please. So our I is this one, zt. Remember, zt is this function. All right. And we would like to evaluate this function, find an upper bound and find a lower bound, see if it doesn't match somewhere. Next, please. Yeah. So lower bound is quite easy. All right. Usually lower bound estimations of these integrals are pretty easy. It only involves application of Cauchy's theorem. All right. So you look at t to 2t, write it as, half plus it. So z of half plus it, integral t to 2t, zeta of half plus it as change of variable half plus it to half plus 2it zeta s ds, and then move the line of integration to the right and apply Cauchy's theorem to the rectangle. All right, and use the bounds of zeta function. Okay, zeta function is bounded by some polynomial in t in the critical strip. Use that information. It's easy to show that. Next slide, please. The lower bound, okay, to the lower bound, in fact, is bigger than a constant times t. All right. After all the evaluation of this, you get that the integral is nothing but it plus o of 1. All right. And therefore, t to 2t mod zt dt is bigger than some constant times t. This is the lower bound. All right, for z of t. Now we need to find an upper bound. Next, please. Okay. Now, therefore, what is our aim? We want to find an upper bound for that integral. All right, of the type t to the power alpha. Now, lower bound we have already got, namely constant times t. Therefore, in order to arrive at a contradiction, we must, previous. Yeah, in order to arrive at a contradiction, we must show that this alpha must be less than 1. All right. That is our aim. So find an upper bound of this so that it is bounded by some power of t with that power less than 1. Then we are in business. Next, please. Yeah. Therefore, okay. Now absolute value of zt dt is less than or equal to t to 2t zeta of half plus it. Okay. because chi of half plus it is 1 in absolute value. Now, one way of looking whether you will get a t to the power alpha, what alpha you are going to get is whenever you have an integral of this type, first apply trivial estimation. All right, say trivially. Now, even if you assume Lindelof hypothesis, it's a hypothesis which is a consequence of Riemann hypothesis. It says that zeta of sigma plus it is bounded by a power of t to the power epsilon. All right, whenever sigma is bigger than or equal to half. Even on that assumption, which is, we don't know whether Lindelof hypothesis is true or not. So even on that assumption, what you get, the estimation of this integral is zeta of half plus it is t to the power epsilon, and the length of the integral is t to 2t. That will give you a t. So the total upper bound is O of t to the power 1 plus epsilon. But we wanted an alpha which is less than 1. So even on Lindelof hypothesis, trivial estimation doesn't give us, the required bound. Therefore, we must do the estimation very, very carefully. All right. Next, please. Okay. Therefore, the aim is to estimate this integral carefully. All right. Not take trivial upper bound. Don't take absolute values. Now, there are two ways of estimating this integral classically. One is either you move the line of integration to the right, all right, of the line sigma is equal to 1. We are on the line zeta of half plus it. You see, zeta of half plus it is inside the integral. Okay, so you move it to one line, to the right of one line. Or what you do is you use some formula for zeta of half plus it and see whether you can get a bound. All right. So there are two ways. Either you move the line of integration to the right or stay on the line. Next slide, please. Stay on the line half and use this kind of formula. This is a formula with finitely many terms and up to square root of t with a very good error. All right. Use some formula like this and estimate it. You'll see that the upper bound is alpha, t to the power alpha with alpha less than 1. Classically, this is done, but it requires the use of, Riemann-Seeger formula or moving the line of integration to the right of 1. Okay, next, please. So there is a new approach which was recently invented, and this uses the first order approximation. You don't have to do hardcore complex analysis. Okay, you just approximate it by using first principle. So this is a standard result. Okay, not very difficult to prove. Namely, zeta of s is summation n less than or equal to x, n to the power minus s, with this error. These are the error terms: x to the power 1 minus s by s minus 1 plus O of x to the power minus sigma. So you truncate this zeta series at the point x with this error term. All right. Therefore, when s is equal to half, you will get equation number 17. All right. So this was, this approach was recently done by my student Usha recently in 2016, and this is available in Hardy Ramanujan journal. Next one, please. So using this one, it is very easy to derive, lower bound. You don't have to do, you don't have to apply Cauchy's theorem and all these things. Just take that series, plug it inside zeta of half plus it. So when you plug it in half plus it, you will get t to 2t zeta of half plus it dt as t to 2t, the first term plus this second sum plus the error. All right. And the one will give you t, and the second sum is small, t to the power half. And therefore, in total, the lower bound is bigger than a constant times t. All right. So t to 2t, zt dt, mod zt dt is bigger than constant times t. Next, please. Again, the upper bound estimation is also not very difficult. All right, it is much simpler than the classical methods. Apply the first approximation formula to the function z of t. Remember, z of t is nothing but chi of half plus it to the power minus half times zeta of half plus it. So you get 21, equation 21. The O terms you see, t to the power half by small t, and this t is between capital T to capital 2t. Therefore, the O terms are very small. Okay. And therefore, now what you need to estimate is essentially the first term. Therefore, integral z to dt, zt dt is nothing but integral of the first term. All right. These are the Stirling formulas for the gamma function which are used. Next, please. Okay. So once you use the Stirling formula and all these things, you get this sum, e to 2t, and then summation n up to t. And inside sum, you get these factors. Now, errors are very small. What you need to estimate is essentially expression 24. This is the crucial sum. All right. The crucial sum is again estimated depending upon where is n. Okay, n is up to t, but there are some points where the integral may become very big. Okay, you have to be very careful about those points, which is called saddle points, where f prime nt is 0. Okay, and so you have to judiciously estimate this integral first, and this integral is estimated by using the standard exponential integral techniques. Next, please. Namely, these are the integrals. These are very nice results on estimating exponential integrals. For example, a to b e to the power I fx dx. If you take trivial upper bound, you will get b minus a, length of the integral, because inside thing is 1, absolute value. But if you know the behavior of f prime, that it is monotonic, and you know the lower bound or upper bound of f prime, then you can save much more. That means you can estimate it very nicely. Similarly, if you have gx e to the power I fx, and if you know the properties of gx by f prime, then you can do very nicely. You can estimate it very nicely. Next, please. Okay. Now, supposing you don't know about f prime, but you know about f double prime, then you can use these theorems. All right. Next, please. Next slide, please. Yeah. So using those, exponential techniques, what you do is you estimate the crucial sum, which was in 24, and you show that that is not very big. That is O of t to the power 3 by 4, that is 26. Okay, this is part of the sum, which is n is up to square root of t. See, our sum was up to t. So we have split it up to square root of t. Next slide, please. And from square root of t to t, you use the next exponential sum, and you show that it is small. It is O of t to the power half. Therefore, in summary, the upper bound is about O of t to the power 3 by 4. See, the lower bound is bigger than t, whereas the upper bound is, there are points where the upper bound is t to the power 3 by 4. Therefore, it contradicts the basic equality assumption, and therefore it shows that there is a 0 of z of t in t to 2t. Okay, which means there is a 0 of Riemann zeta function on the half line between t to 2t, and therefore, since t was arbitrary, it shows that Riemann zeta function has infinitely many zeros on the line half. This is the complete proof of Hardy's theorem. Next, please. Therefore, now once you have Hardy's theorem, you would like to know whether you can prove a similar theorem for more general L functions. All right. So there is a class of function which is a generalization of Riemann zeta function. So Riemann zeta function is given by summation 1 by n to the power s. It has analytic continuation into the entire complex plane except for s is equal to 1. Riemann zeta function satisfies functional equation, and based on these properties, Selberg he constructed a class of functions having properties similar to Riemann zeta function. That class of functions is called Selberg class. All right. You can think of Riemann zeta function as at the back of your mind. All right. Next, please. So the basic question is, given a function, so there is something called degree associated with each function. It's an important thing. All right. Riemann zeta function is of degree 1. And the degree is defined in terms of 2 times summation of lambda I. What is this lambda I? Previous slide, please. Previous. So lambda i's are nothing but the coefficients of this gamma lambda is plus mu I. The coefficients of s in the functional equation. All right. So this lambda i's, look at all the lambda i's, take the sum, multiply by 2, you will get the degree. For example, in Riemann zeta function, you have s by 2. Therefore, Riemann zeta function is of degree 1. If you have only gamma s, that's of degree 2. Next, please. So this is one big conjecture which says that degree of a function is a positive integer. It's a big open conjecture. We don't know the truth of this. All right. Now the question that is relevant to our lecture today is that given a function of degree d, you can show that it has infinitely many zeros between, in the strip 0 to 1, a real part of s between 0 and 1, that infinite strip. If you take a rectangle with sides 0 and 1, infinite rectangle, then one can use analogous theory like Riemann zeta function and show that any function of degree d has infinitely many zeros. But Hardy's theorem will ask whether it has infinitely many zeros on the critical line, on the central line. Next, please. So therefore, given a function f in the Selberg class, does it admit infinitely many zeros? All right. And this question is known for all examples of degree 2, degree 1 functions. All right. Yeah, one of the problem is find out all functions of degree 2 in the Selberg class. This is not known. We don't know all functions of degree 2. We know few functions. Next, please. For example, zeta square is in degree 2. Product of 2 L functions is in degree 2. Okay. LFS is in degree 2. If you take a Dedekind zeta function of quadratic number field, then it is in degree 2. All right. Next, please. So for all those functions, we know that there are infinitely many zeros. But the question is, take any typical degree 2 function, does it admit infinitely many zeros? Next, please. So these are some preparations of, analogous to what we did for Hardy's function, Hardy's Z function. Next, please. Next. Yeah. So if you take any degree 2 function, assume that the coefficients an squares. Okay. The degree 2 function is an by n to the power s. Okay. Summation f is summation an by n to the power s, and it is degree 2. And if the AN satisfies this condition 29, then we were able to show that Fs has infinitely many zeros on the critical line. Real part of S is equal to half. So this is the only theorem available so far on extension of Hardy's theorem. All right. So one would like to extend it. Next, please. To other functions. Next, please. Yeah. So you see the crucial sum that comes, okay, in the evaluation of these things is upper bound. As I said, lower bound is pretty easy. All right. Lower bound is not difficult. One has to estimate upper bound to arrive at a contradiction to the lower bound. In the degree 2 function, you know, this one was the crucial estimate. Summation an e to the power minus 2 pi I n by square root of q, where n is between, you know, t to 2t, roughly saying q1 times t to 2 times q1 times t. The q1, q2 are some numbers. All right. So if you can show that this sum is small, okay, then you have a theorem. Then you have Hardy's theorem. And this is what was difficult. But luckily, Debussy and Dillon, they have shown that if you take any multiplicative function, all right, and suppose fn square, f is multiplicative means f of n times m is f of n times f of m, whenever n and m are co-prime. So if you have summation of fn squares as O of x, okay, so on an average, if they are not very big, then the exponential sum fn e to the power 2 pi I n alpha for every rational alpha is very small. The average is very, very small. This is little O of x. I hope you understand what is capital O and little o. Capital O, so f is capital O of g means f by g is bounded in absolute values. Okay. And f is little of g, f of x is little of gx means fx by gx goes to 0 as x goes to infinity. All right. So under 30, so if you have fn square is O of x, then they showed that this exponential is small, and therefore, you know, our result follows. So we were able to use this theorem and show that this exponential sum an e to the power minus 2 pi I n square root of q is small, and therefore Hardy's theorem is true for any degree 2. Next, please. Now the question is, what about degree bigger than 2? Okay, next, please. Next. One more. Yeah, okay. So when the degree is between 0 and 4, all right, with Anirban and my former student Krishnan, we were able to show that if this sum 32, sum in 32, an by n to the power half minus 1 by d times e to the power I d n to the power 2 by d by 2q, if this is small, when n is between t to the power d by 2 times 2 to the power 2 times t to the power d by 2. D is the degree, and degree is less than 4. All right, between 2 and 4. So if the degree is, if this exponential sum is small, then Hardy's theorem is true. So we have a result for on Hardy's theorem for Selberg class up to degree 4 under the condition 32. All right. So one of the open problems here is take any degree 3 function and show that 32 is true. Then you have a theorem. All right. Take any degree 3 function and show 32 that this holds. All right. Next, please. Now, thing is, if ANs are not multiplicative, then what happens? All right. So as you have seen in the lectures of Professor Brindavan Sahu and the previous by Professor Stephen Miller, the L functions associated to modular forms. So these are L functions associated to cusp form for gamma naught n of half integral weight. So take LSF, an by n to the power s. They have nice analytical properties, all right. However, they do not have Euler product, all right. So not having Euler product means the coefficients are not multiplicative. And also not having Euler product means Riemann hypothesis is also false, all right. Next, please. But, okay, are there infinitely many zeros on the critical line? So in a joint work with Jaban and Sudhir, we were able to show that take any function, half integral weight cusp form for gamma naught 4, okay, and suppose it's an eigenform for Tn square, and also, you know, for the involution, Fourier involution, you know, is if you have f belongs to this, you take any f, okay, and the Fourier involution is defined by this one. Next, please. Next slide, please. Yeah, so the result is previous. The result is the following. So take any function which is an eigenform for all Hecke operators Tn square and the operator W4, which was defined in the previous slide. Assume that the previous. This is a W4 operator. All right. Now assume that. Next, please. Next. Assume that all Fourier coefficients ans are either real or purely imaginary. This condition we require it because we want to use the Hardy's ZT function. ZT is Z bar T. For that, either you need to have ans to be real or purely imaginary. Okay. Then the L function attached to f has infinitely many zeros on the critical line. So then the Hardy's theorem is true for this. All right. Next, please. Here again, the crucial thing was upper bound estimation. Lower bound is pretty easy again. And upper bound estimation for this sum when n varies between t to 2t. Okay, t by pi to 2t by pi. You show that this sum is bounded by t to the power half. All right. And that was done by using a theorem of Ivaniev, okay, who said that if you have any half integral weight cusp form, then for any real theta, the exponential sums are bounded by x to the power k plus half by 2 log 2x. And this, applying this one by partial summation, our upper bound follows. All right. So these are the some of the extensions of Hardy's theorem that we were able to obtain. In fact, Sudhir and Jaban, they have extended this to many more L functions and also improvements on these previous results. All right. So there is a lot of work that is being done on looking at L functions and trying to show whether Hardy's theorem is true or not for that. This is one theme of ideas which has led to a lot of development. Okay. And there are several other problems related to zeros of the Riemann zeta function that I have not discussed. For example, when you look at, there are infinitely many zeros. The thing is, if you look at t to 2t, capital T to capital 2t, how many zeros are there? All right. And how many, so what portion of this critical zeros coincide with all the zeros in the string. That means, you know, how do you compare? Okay. What Selberg has proved is that the number of zeros, if you take any, you know, box of length t, I will just take 2-3 more minutes and then I will finish it. The other theme of, you know, research that is going on is on the proportion of critical zeros. How many, you know, compute the number of zeros. Well, let me say it this way. We know that if you look at the box of height t, then the number of zeros of Riemann zeta function, total number of zeros, are about t log t. All right. What proportion of zeros that we know? N0t. What proportion of critical zeros we know? So Selberg proved that 1/3 of zeros, there is a constant A said that the number of zeros on the critical line is bigger than A times T log T. And there is a lot that has led to a lot of research. Another theme is between gaps between zeros. We have some results on that. Maybe some other time I will discuss on that. So this is a very rich subject, Riemann zeta function and its zeros. Okay. Today, in today's discussion, we have only discussed about Hardy's theorem and its extensions and analogues to other L functions. So I think I will stop it here. If you have any questions, I will be happy to answer. Thank you very much.
Thank you, sir. I am Uttal Kesari Datta, the co-convener of this webinar and assistant professor of Department of Mathematics, KIIT deemed to be university. It's my honor to take the opportunity to extend thanks to the speaker, Professor Kottada, for such an informative talk on the zeros of Riemann zeta function and its analogues. Sir, your talk was so thought-provoking. It really made us think. We enjoyed a lot your session, sir. Thank you, sir.
Thank you.
So we have some questions. I would like to address these questions. This one question from Pinaki Prasad Kaur. Yes, there is Euler-Rayleigh method to find the bounds for the smallest zero for orthogonal Bessel functions. Can we use this method in calculating the bounds for smallest zero of this zeta function?
Hello?
Yes.
I'm not able to hear.
Yes, sir.
Smallest zero.
Yes.
We know the smallest zeros. We know the smallest zero. Okay. Riemann was the first to compute the smallest zero. That is 14.117, something like that. It's on the line half. The first zero comes about on the line around 14. And the second zero also, we know zeros. I mean, you might have seen in Professor Stephen Miller's talk that we know zeros of 10 to the power 20th zero, we know.
Yes.
All right. They're all on the line half.
So one more question, sir.
Yeah.
Sir, what about the What about the irreducibility of zeros of L functions attached to modular forms of half integral ones?
What do you mean irreducibility of zeros means what?
Means over a field.
Yeah.
It means for zeros of L functions.
Yeah.
Attached to modular form of any half integral weight. So what is the irreducibility of that case?
No, I don't understand irreducibility of that function. What do you mean by irreducibility of function?
That means when
see, you are looking at half integral weight function. You are looking at half. See,
Yes.
you are looking at half integral weight L function, right?
Yes, sir.
Okay. That belongs to some subgroup. Okay.
So
Over
this is some automorphic representation of a polar form.
So see, not much results are known about zeros itself. You know, this is the first result that we have got for half integral weight. All right. So the subject is very rich.
Just any more questions from the audience?
Hello.
Yeah.
Thank you, sir, for this wonderful talk. I had this small doubt, sir.
Yeah.
It's regarding the zeros of Riemann zeta function.
Hmm.
We saw that some trivial zeros of Riemann zeta functions are when t is equal to some some negative even integers. So similarly, the critical line means in the critical line, Hardy showed that there are infinitely many zeros of the Riemann zeta function. But
Right.
But has he given some like this for this value the zeta function is specific value? Has he
No,
given
I mean,
some?
no, you can't find exact value. What you do is, this is, you know, you take an interval because you are comparing the, when you say that a function has a zero, that means zero at a, okay? You have a zero, so take a function f. You say that f of a is zero, which means what? When, since the function is continuous, to the left of a and to the right of a, the signs are different, right?
Yes, sir.
Is it? So that is how, you know, the zeros have been found. So you take a value, okay, find the value of the function, whether it is positive or negative. All right. So once you have to the left negative, to the right positive, then you know that there is a zero in between. So keep on refining your estimation. Then you get that 14.1, then 14.142, then 14.123 and some, okay? Exactly, you can't say that at this, you know, it's not a rational number that at this point you have a zero. All right.
Yes, sir. Sir, one small doubt I had. Sir, when we talk about like infinitely many zeros, so is he saying that there are uncountably uncountable number?
No, it's an analytic function. Okay. So it you can't have uncountably many zeros.
It will have uncountably many zeros.
I mean, so
thank you, sir.
Yeah.
Any more questions? So let's thanks again, Professor Kotada, for this splendid presentation. On the behalf of Department of Mathematics, KIIT deemed to be University, I really appreciate and want to express my sincere gratitude to the speaker, Professor Kotada, who has spared valuable time from his busy schedule to grace this event and enlighten all of us. Once again, thank you, sir.
Thank you very much.
Thank you, Professor Srinivas, for your valuable time. Thanks again.